There is a secret hidden all around you, right now, in this very moment, a secret quietly woven into the fabric of reality itself. You cannot see it with your eyes, nor touch it with your fingers, and yet it shapes every part of your existence, every atom in your body, every star in the cosmos, moves within spaces you've never known were there. Imagine for a moment if you could step beyond the world you've always known, beyond length, width and height. Imagine stepping out of time itself and drifting freely through invisible realms, dimensions hidden just beyond your senses. What would it feel like to glimpse the fourth dimension, or the fifth, to see entire universes unfolding side by side, realities branching like rivers, and infinite worlds waiting just beyond reach? Tonight, together, we'll journey into the deepest mystery of modern science. We'll venture through hidden corridors of the universe, guided by groundbreaking theories and astonishing discoveries that reveal higher dimensions as real as the breath you're taking now. This journey might change forever how you see your reality. Before we begin our voyage, if this kind of journey speaks to you, if the quiet mysteries of science and the mind stir something deep within, a like, a comment, or a simple subscription makes a world of difference for a small channel like mine. It helps keep this space alive and brings this gentle curiosity to others who might be searching for it too. So relax, open your mind, and allow yourself to drift beyond what you've known as we step gently into the hidden dimensions of our universe. We live comfortably within the embrace of three familiar dimensions: length, width, and height. This space we call home shapes every moment, every experience. We walk through rooms, gaze at distant mountains, reach upward into the sky, each action effortlessly bound within the reassuring framework of three-dimensional reality. But what if our universe is not so simple? Science tells us that reality itself may hold secrets, dimensions hidden like gentle whispers beneath the loud symphony of ordinary life. Time, the elusive fourth dimension, weaves seamlessly alongside the three dimensions we can touch, crafting a delicate tapestry known as spacetime. Here, every moment you've lived, every memory you've ever held, sits suspended, quietly coexisting in an intricate dance. Beyond time, however, the mysteries deepen. Physicists speak of fifth and sixth dimensions, gateways to parallel universes, bridges to alternate realities, paths untaken. Entire worlds, strangely familiar yet intriguingly different, exist side by side with our own. Could there be versions of ourselves living lives we can barely imagine, hidden only by the thinnest veils? And still deeper we journey, through dimensions curled invisibly within the tiniest scales of existence. String theory, one of science's boldest dreams, whispers to us of 10, even 11 dimensions, intricately folded, waiting patiently within the heart of every atom, woven into the fabric of every star. Tonight we'll explore these extraordinary realms, guided by wonder and the cutting edge of scientific thought. We'll unfold the layers of reality, step through dimensions unseen, and marvel together at the breathtaking architecture of existence itself. Allow your thoughts to expand, your awareness to soften. As you drift through this deeper understanding of space and self, know this: you're standing at the threshold of something vast and beautiful and hidden in plain sight. Welcome to the hidden dimensions. To begin our journey into higher dimensions, we first must understand what a dimension truly is. Imagine yourself sitting quietly in a room, perhaps the very room you rest in now. Look around softly. Notice the length of the walls, the width of the floor, the height of the ceiling. You are intuitively aware of three dimensions, as natural to you as breathing, as constant as your heartbeat. Every moment of your life unfolds comfortably within this familiar geometry, the reassuring space you call home. Yet what precisely do we mean when we speak of dimensions? Dimensions are, at their essence, measurements of freedom, directions in which movement and existence are possible. A single dimension is simply a straight line, a continuous path without breadth or depth. Imagine walking along a long straight road that stretches infinitely ahead and infinitely behind, but nowhere else. You can move forward or backward, but not to the side. This world is simple, yet profoundly limited. Now picture two dimensions, a flat plane, like the surface of a vast ocean, infinitely wide in all directions. You could travel forward, backward and sideways, but never upwards or downwards. Imagine beings who lived their entire existence on this flat expanse, unaware of a world beyond their two-dimensional home. They would never understand concepts like above or below. Their reality would be simple, yet incomplete, full of mysteries they could sense but never explain. To these two-dimensional beings, a visitor from the third dimension, a person like you, would seem like magic, appearing and disappearing at will, able to see into their enclosed spaces, effortlessly performing tasks they perceive as impossible. To them you would be a being of immense mystery, moving freely in a direction they could scarcely imagine. And yet you exist comfortably within 3 dimensions, aware of length, width and height, effortlessly navigating spaces that would utterly confound our hypothetical 2-dimensional friends. You can lift your hand upward into the air, walk across the ground, move forward or backward at will. To you, this freedom feels obvious, natural. But what if your own perception, your own freedom is just as limited, simply unaware of other directions beyond your reach? Scientists ask us to consider exactly that. They invite us to look beyond the confines of our everyday experiences, beyond what we can easily visualize. Imagine for a moment there are other dimensions, extra directions in space, hidden in plain sight, awaiting our awareness, like secret corridors tucked neatly into reality itself. What if our world, just like that flat 2-dimensional universe, is merely a shadow, a fragmentary glimpse of something much deeper, richer, and astonishingly more complex? This profound question isn't purely philosophical or imaginary. It lies at the heart of modern physics. Scientists have found clues, scattered throughout nature, subtle hints that our 3-dimensional existence, our comfortably familiar universe, may be only a part of the larger story. In physics laboratories around the world, scientists carefully explore how extra dimensions might reveal themselves. They probe mysteries such as gravity's subtle behavior, the strange dance of quantum particles, and the astonishing regularity of cosmic constants. And increasingly, evidence suggests that dimensions beyond our everyday perception might hold keys to some of our deepest scientific puzzles, quietly shaping our lives in ways we have only begun to understand. As you listen tonight, allow yourself to soften your grip on the familiar. Allow your imagination to gently stretch beyond the comfortable borders of length, width, and height. For in doing so, you begin the first careful steps into dimensions unknown, worlds hidden quietly beyond your ordinary sight. Let your breath slow, your mind ease into curiosity, as you prepare to travel deeper, into dimensions unseen, into the gentle mysteries awaiting in the darkness beyond our familiar space. And as we move forward, we'll discover that the universe is far larger, far richer, and far stranger than we ever dreamed possible. Consider now the idea of space itself, the invisible stage upon which the universe's grand drama unfolds. To you, space feels open and obvious, a continuous canvas on which the galaxies swirl, planets spin, and life thrives. Yet for centuries, humans assumed their intuitive view of space was complete. They believed their eyes and minds saw reality clearly, fully comprehending the fundamental structure of existence. But reality, it seems, holds its secrets closely. History has repeatedly shown that human intuition, while powerful, is often incomplete. Imagine once more the 2-dimensional beings living flat upon a sheet of paper. Their perceptions, though sharp, would be forever confined. To them a cube, something simple for you to hold in your hand, would appear as a shifting shadow, impossible to fully comprehend. Their minds would struggle to grasp its reality, forever bound by their limited perspective. And here, dear listener, is the gentle yet profound truth. We ourselves may be just as blind to higher dimensional shapes and realities hidden quietly around us. Science, through mathematics and experimentation, has begun to illuminate these invisible dimensions, opening doors once thought impossible to reach. Einstein revealed to us that the very fabric of our reality includes time as a fourth dimension, intricately woven together with space. In this unified tapestry, spacetime, time and space are not separate entities, but intertwined strands that influence each other profoundly. Think of yourself now, quietly drifting through time. Each heartbeat, each breath carries you forward through this unseen dimension. You cannot step backward into the past or leap instantly into the future. Yet, from a higher dimensional viewpoint, your entire lifetime would appear as a continuous path, stretching beautifully across space-time, much like a trail winding gracefully through a vast landscape. But science does not stop at the fourth dimension. Theoretical physicists, driven by curiosity and wonder, have discovered that to fully explain the universe, to reconcile gravity with quantum mechanics, more dimensions may be necessary. Dimensions beyond time, beyond our direct perception. Imagine, for a moment, dimensions curled into tiny loops or folds, invisible and infinitesimal, tucked neatly into the very structure of reality itself. Like delicate origami hidden within every particle, these compactified dimensions influence the behaviors of atoms, photons, and electrons, shaping every moment of your life without your knowledge. Mathematically, these higher dimensions are no less real than length, width, or height. Equations of extraordinary elegance and complexity describe spaces with 6, 10, even 11 dimensions. These spaces may be inaccessible to our senses, yet their existence could hold answers to questions as deep as why gravity feels so weak compared to other fundamental forces, or how the cosmos itself emerged from the primordial void. Consider again the shadow cast by the three-dimensional cube onto a two-dimensional surface. In the same way, our three-dimensional reality might merely be a shadow, a projection of something far grander unfolding in higher dimensions. Every star, every galaxy, every event across the universe could be the visible echoes of hidden structures lying just beyond our reach. Tonight, we are travelers, explorers stepping beyond the familiar. As your breathing slows and your body relaxes deeper, gently release the limitations of intuition. Allow yourself to sense, if only vaguely, the profound possibilities whispered to us by modern science. Our journey has only just begun. Ahead lies deeper exploration. The fourth dimension of time, the branching paths of the fifth dimension, and realms even stranger and more wondrous beyond. As your mind opens, softly embracing the unknown, rest assured that each step is guided carefully, gently, and poetically into these hidden realities, ready to reveal the universe's most beautiful mysteries. And now, let yourself drift softly onward, into the next dimension, where the journey grows richer and the discoveries more wondrous with each gentle breath. Let us journey deeper now, beyond the three familiar dimensions of space, and step gently into the embrace of the fourth dimension, time itself. Time surrounds you softly, always present, yet impossible to touch. You feel its gentle passage with each heartbeat, each slow breath, and each quiet shift from past to present, present to future. It flows continuously, invisibly shaping everything you've known, yet you can never hold it still in your grasp. But what is time truly? In everyday life, time feels as straightforward as the ticking of a clock, a steady stream flowing only in one direction, from yesterday toward tomorrow. Yet, as gentle as this perception is, science reveals that time is far more mysterious, far more subtle than it appears. Time, according to Albert Einstein, is not separate from space. Instead, the two form a seamless fabric called spacetime, a unified structure that bends and curves under the weight of mass and energy. Imagine spacetime as a vast elastic canvas stretched across the universe, gently curving around planets and stars. Wherever mass exists, spacetime bends softly around it, creating what we perceive as gravity. You might picture the Earth resting gently upon this flexible cosmic sheet, creating a subtle indentation. The Moon moves around our planet, guided by the gentle curvature created by Earth's mass. Similarly, planets orbit stars, their graceful paths defined by the invisible curves in spacetime itself. But what does this mean for us, for our own perception of reality? Einstein's insight teaches us something profound. Time does not pass equally for everyone. Instead, it flows differently, depending upon your speed and the strength of gravity around you. This remarkable effect is known as time dilation, and it's not merely theoretical, it has been tested and proven again and again. Imagine two identical clocks. One stays here on Earth, while another travels aboard a spacecraft, racing gently across the cosmos at nearly the speed of light. When the travelling clock returns, it will show less time has passed. Time itself has slowed aboard the fast-moving vessel, stretching moments into longer intervals. Time also moves differently in strong gravitational fields. Imagine standing on the surface of a massive planet or near a black hole, where gravity is extraordinarily powerful. There, each second might pass far more slowly than it does here on Earth. An hour spent near a black hole could correspond to many years passing elsewhere in the universe. These strange truths are not merely ideas, they shape the fabric of reality itself. Our satellites, carefully orbiting high above the Earth, must constantly correct for these subtle differences in time to guide us accurately via GPS. Without accounting for Einstein's discovery, our technology and our modern lives would drift slowly, softly, out of sync. Yet these subtle differences are rarely noticed in everyday life. Our gentle existence moves at a speed far too slow, and gravity around us is far too mild for these effects to become obvious, and so time feels familiar, predictable, gentle, a comfortable companion whose secrets remain quietly hidden beneath ordinary experience. But tonight, as you drift toward rest, imagine lifting gently from your ordinary life, moving faster and farther into realms where these subtle differences become clear, vivid, and beautiful. Imagine seeing time stretch and slow, like ripples on a pond, guiding your journey deeper into the mysteries hidden within this fourth dimension. As your breathing eases into soft rhythms, your mind gently opens to this expansive truth. Time is not fixed and rigid, but delicate and flexible, a dimension woven intricately with space, inviting you deeper into understanding, deeper into relaxation. And with every calming breath, you slip further into the embrace, ready to discover even greater wonders that lie quietly ahead. Time, once thought absolute and universal, has become a far richer and more nuanced dimension since Einstein's discoveries. But the implications of understanding time as a true fourth dimension extend far beyond clocks and gravity. They challenge the very foundations of how we perceive reality itself. Consider again the concept of space-time, a unified fabric combining space and time into a single, seamless structure. Within this structure, all events that have ever occurred or will ever occur exist simultaneously as coordinates, points mapped carefully within the four-dimensional landscape. From this perspective, the past is not truly lost, nor is the future waiting uncertainly to emerge. Instead, every moment, past, present, and future, exists concurrently, spread across the space-time continuum. Your life could be imagined as a long, winding thread, weaving through this fourth-dimensional tapestry. Each experience, from your earliest memories to your imagined future, occupies a distinct location within space-time, ever-present and permanent. But if every moment already exists, why do we only perceive time as flowing forward? This profound question has captivated scientists for generations. The answer, intriguingly, may lie in the second law of thermodynamics and a concept known as entropy, a measure of disorder or randomness. Entropy increases naturally as energy moves from states of order toward chaos, from structure toward randomness. An egg can break but not spontaneously reassemble. Ice melts into water but does not spontaneously freeze back into perfect cubes without external influence. It is this natural tendency toward greater entropy that gives us what scientists call the arrow of time, a directional flow guiding our experience clearly from past toward future. Yet fundamentally, the equations that describe the universe do not require this forward-moving arrow. The laws of physics are essentially symmetrical, working equally well forwards or backwards. Time, mathematically, could move in either direction. It's only through the lens of entropy, the unfolding increase in universal disorder, that time acquires its directional quality, always forward, never backward. This raises a fascinating possibility. Could there exist regions of the cosmos, or even entirely different universes, where entropy decreases, reversing the arrow of time? In such worlds, the inhabitants might perceive their universe in ways utterly alien to our intuition, watching eggs spontaneously reassemble, shards of glass forming seamless windows, or scattered stars gently coalescing back into nebulae. Moreover, time's elasticity can be observed dramatically near cosmic extremes, such as black holes, the universe's most mysterious gravitational objects. Approaching a black hole's event horizon, the boundary from which nothing escapes, time slows dramatically relative to a distant observer. If you could safely hover just outside this horizon, you'd witness the universe around you accelerating rapidly, as if watching the fast-forwarding of cosmic history. Entire galaxies would age and fade, stars would ignite and extinguish, civilizations could rise and fall, all within what felt like mere moments to you. Inside the event horizon, our known laws of physics begin to unravel. Time itself might twist or exchange roles with space, creating scenarios impossible to imagine clearly. Within these extreme conditions, theoretical physicists speculate about phenomena like wormholes, hypothetical bridges through spacetime that might allow travel between distant points in the universe or even between entirely different times. While still theoretical, wormholes are solutions permitted by Einstein's equations. If they exist, they would profoundly alter our understanding of reality, potentially enabling journeys through time and space that challenge our deepest intuitions. Yet they remain tantalizingly elusive, existing only on paper and in speculative imagination. Even subtler effects of this fourth dimension shape our everyday experiences. Einstein's insight that time moves slower near massive objects means your head, located farther from Earth's gravitational center, ages ever so slightly faster than your feet. Over a human lifetime, this difference is negligible, mere billionths of a second, but it reveals the elegant complexity woven quietly into everyday existence. Thus, time emerges as a dimension far richer and stranger than simple clocks and calendars suggest. It shapes our understanding of reality, our universe, and perhaps even multiple universes. From the gentle ticking of a watch to the immense gravitational pull of a black hole, the fourth dimension guides everything we've known, quietly directing the symphony of cosmic events and human experience. As we venture further into higher dimensions, we move beyond the limits of space and time into worlds even more astonishing, where the fabric of reality itself is stretched in ways we are only beginning to comprehend. Beyond the fourth dimension of time lies a realm even more intriguing and profound, the elusive fifth dimension. To grasp this dimension clearly, we must step further outside our intuitive understanding, venturing into realms where reality splits into countless possible pathways and parallel existences. Imagine your life as a river gently flowing downstream, each decision creating subtle currents and eddies, shaping the direction of your personal journey. You might choose one path over another, a career, a relationship, a place to call home, each choice carrying you steadily forward along a unique route through space-time. But what if every choice you didn't make, every path left untraveled, continued to exist, branching off invisibly into its own separate reality? In the fifth dimension, precisely this scenario unfolds. Here, reality splits and branches, creating parallel worlds that coexist simultaneously, though each remains invisible and inaccessible to the others. This isn't merely speculative fantasy, it aligns closely with modern interpretations of quantum mechanics, most notably the many worlds interpretation. Quantum mechanics tells us that the universe at its fundamental level behaves not as solid objects moving predictably, but as clouds of possibility and probability. At each quantum event, Every microscopic choice made by particles, every tiny fluctuation, reality does not collapse into a single outcome, but instead unfolds into all possible outcomes simultaneously. Each outcome, each quantum possibility, creates an entirely new branching universe. This idea of parallel universes might seem deeply counterintuitive, even startling. Yet, mathematically and scientifically, it solves several puzzles that have long troubled physicists. Instead of forcing reality to select only one outcome from many possibilities, the universe allows every possibility to occur, elegantly resolving paradoxes that arise in quantum theory. Consider a simple example from everyday life. Imagine flipping a coin into the air. When the coin lands, you see either heads or tails, a single clear result. But within the framework of the fifth dimension and the many worlds interpretation, the moment the coin lands, reality branches into two distinct universes. One universe in which you see heads, and another, parallel universe in which you see tails. Both universes are equally real, equally valid, though each remains forever inaccessible to the other. Extend this concept now to every decision you've ever made, every chance you've encountered, every subtle choice that shapes your personal experience. For each decision, countless parallel universes branch off, each world quietly coexisting alongside the others, each containing a slightly different version of yourself. In some of these parallel worlds, your life may be strikingly similar to your current reality, differing by just a handful of small, unnoticed choices. Perhaps in one universe, you decided to pursue a different career. In another, you moved to a different city. In yet another, you took an entirely different path altogether. Other parallel realities might differ more profoundly, each branching from key turning points, creating lives unimaginably different from your own. From a scientific standpoint, these branching universes provide a compelling way to resolve certain quantum mysteries, such as why particles behave unpredictably at tiny scales, yet consistently form stable structures at larger scales. The many worlds interpretation neatly explains this by showing that all possibilities genuinely occur, spread across countless parallel realities, each consistent within itself. Yet, despite their scientific elegance, these parallel universes remain hidden from our direct experience. We live gently confined within our own stream of reality, unable to observe or travel directly to these other branches. The fifth dimension, bridging these possible worlds, provides the conceptual framework to understand how they might coexist, overlapping like sheets of paper stacked invisibly atop one another. While we cannot step physically into these alternate realities, understanding them allows us to see our own universe more clearly. It transforms how we think about choice, fate, and possibility, reminding us that our perceived reality may be just one facet of an infinitely richer and more complex multiverse. As science delves deeper into this astonishing dimension, experiments continue to probe quantum behavior, testing predictions of parallel outcomes, and searching for subtle clues that might validate or challenge the existence of these hidden worlds. Though still beyond direct human perception, the fifth dimension invites us to see existence itself as infinitely branching, intricately woven with endless possibilities, quietly shaping our deepest understanding of reality. To journey deeper into understanding the fifth dimension, we must carefully consider how science approaches the concept of parallel worlds and branching realities. Though invisible and intangible, these ideas have real and profound implications for modern physics, philosophy, and our perception of reality itself. Physicists explore parallel universes not only through quantum mechanics, but also through the broader fields of cosmology and theoretical physics. The universe we inhabit appears finely tuned, possessing specific values for fundamental constants, such as the strength of gravity, the mass of particles, and the precise expansion rate of the cosmos. Even slight variations in these constants could result in universes radically different from ours, perhaps incapable of supporting stars, planets, or life itself. Why is our universe so perfectly balanced? One compelling answer lies within the fifth-dimensional framework of parallel universes. Perhaps all possible universes, each with different laws and constants, exist simultaneously. We find ourselves living in a universe that supports life simply because only in such a universe could we emerge to ponder these very questions. A philosophical perspective known as the anthropic principle. In this multiverse scenario, universes branch continuously, creating a vast landscape of possible realities, each isolated within its own fifth-dimensional pocket. Visualize a landscape of countless bubbles, each bubble a distinct universe, floating gently within the infinite expanse of higher dimensional space. Some of these universes collapse quickly, others expand endlessly into cold, empty voids. A few, like ours, settle into conditions suitable for complex structures, galaxies, stars, and ultimately, life. Yet how might we detect the presence of parallel universes if we cannot directly observe them? Scientists approach this puzzle through indirect methods, searching for subtle clues in the cosmic microwave background radiation, patterns in cosmic inflation, and anomalies within particle physics. These clues, though faint, may reveal evidence of collisions or interactions between universes, leaving subtle imprints upon our own reality. In recent decades, experiments conducted at particle accelerators like the Large Hadron Collider have tested theories involving hidden dimensions and parallel universes. By smashing particles together at incredibly high energies, physicists hope to glimpse phenomena that suggest the presence of extra dimensions or branching universes, perhaps particles vanishing mysteriously into unseen dimensions or unexpected energy signatures appearing suddenly in their detectors. While no definitive evidence has yet emerged, scientists continue their careful explorations, knowing the slightest hint could revolutionize our understanding of reality. Each new observation, each quantum experiment, edges humanity closer to unraveling the mystery of whether our universe truly stands alone or is merely one among infinite others. Additionally, the fifth dimension offers intriguing theoretical possibilities related to space and time travel. Though speculative, physicists consider scenarios in which the fifth dimension might allow, at least theoretically, travel between parallel worlds. Imagine, if you will, higher dimensional bridges, portals connecting one universe to another, pathways gently woven into the fabric of reality itself. These hypothetical portals, if they exist, could fundamentally alter how we understand distance, time, and the nature of existence. These concepts extend beyond mere fantasy, grounded firmly within rigorous mathematical formulations and theoretical models. Advanced theories, such as those emerging from string theory, propose higher dimensional membranes, or branes, floating gently within a higher dimensional bulk. Within this complex landscape, parallel universes might reside upon separate branes, separated by dimensions we cannot directly perceive. Occasionally, physicists theorize these branes might collide, creating dramatic cosmic events capable of spawning entirely new universes, perhaps even explaining the Big Bang itself. In this framework, our own universe could be just one product of a gentle collision between higher dimensional branes, each event spawning an entirely new cosmic reality. Such theories expand our horizons profoundly, pushing our understanding beyond comfortable boundaries. While these concepts remain theoretical, they highlight the fascinating depth and potential richness of the fifth dimension. Far from mere abstraction, this higher dimensional thinking shapes the cutting edge of modern scientific inquiry, opening doorways to understanding our universe, and possibly countless others, in ways previously unimaginable. As we venture forward into even higher dimensions, our exploration will carry us toward realms even stranger and more extraordinary. With each new dimension, the mysteries multiply, and the universe reveals itself as infinitely more astonishing, intricate, and beautiful than our intuition ever imagined. Having travelled gently through the branching pathways of the fifth dimension, we now take an even bolder step forward, venturing deeper into the profound mystery of the sixth dimension. where entirely new universes come into view. Here, reality expands dramatically, revealing possibilities not merely branching from a common origin, but separated entirely by different initial conditions. In the fifth dimension, we imagined universes branching from every possible decision and quantum event, but all stemming from the same fundamental physical constants, laws, and starting conditions. Each parallel reality might differ only slightly from our own, like alternate versions of a familiar story. But within the sixth dimension, universes become fundamentally distinct, each with unique beginnings and different laws of physics entirely. To understand this clearly, picture for a moment the vast landscape of potential universes, an infinite cosmic tapestry. Within this tapestry, each universe begins as its own distinct patch, defined by its own unique set of physical constants and initial conditions. One universe might have a gravitational force just slightly stronger, causing matter to collapse rapidly into black holes, preventing galaxies and stars from ever forming. Another universe might possess a weaker nuclear force, preventing atoms from forming stable elements beyond simple hydrogen, creating a universe empty of complexity and life. In the sixth dimension, every conceivable combination of physical laws and constants exists simultaneously, spread across infinite possibilities. These universes are not mere variations of our own reality, but profoundly different realms, each separated by the very foundations of their physical existence. Scientists often call this expansive idea the landscape multiverse, a theoretical construct drawn from modern cosmology and string theory. In this model, each universe occupies its own point within an enormous, multidimensional space. Some universes are vibrant and dynamic, hosting galaxies, stars, and life. Others remain barren, cold, and dark, unimaginable landscapes dictated by strange laws we might scarcely comprehend. But what exactly determines these fundamental conditions in each universe? Physics suggests that these constants, such as the strength of gravity, the speed of light, and the charges and masses of fundamental particles, may be influenced by subtle interactions of higher dimensional structures, such as strings and branes. String theory, one of modern science's most ambitious frameworks, describes particles not as point-like dots, but rather as tiny vibrating strands of energy. These strings vibrate in higher dimensional spaces, with each mode of vibration corresponding to different particles and forces. The particular way these extra dimensions are folded, curled invisibly within themselves, determines precisely how these strings vibrate, shaping the fundamental physical laws and constants of each universe. In the sixth-dimensional landscape, these curled dimensions might vary dramatically from one universe to the next, leading to entirely distinct laws of physics. In some universes, gravity could behave differently, matter might form in entirely alien ways, or even the concept of dimensionality itself might change profoundly. The possibilities, mathematically speaking, are virtually limitless. Consider for a moment universes so radically distinct that even concepts as fundamental as space and time become profoundly altered or even meaningless. In such realities, dimensions might fold or overlap differently, or additional exotic forces might emerge, creating worlds that stretch our imagination beyond its very limits. Scientists explore these astonishing possibilities not merely as fanciful speculation, but as rigorous theoretical scenarios. Through advanced mathematics and cosmological modelling, physicists strive to understand how these vastly different universes might emerge naturally within higher dimensional frameworks. The equations guiding this exploration reveal an extraordinary diversity of realities, each internally consistent, yet vastly unlike our own. While the sixth dimension itself remains impossible for us to physically access or directly observe, its existence profoundly impacts how scientists think about the origins and structure of our universe. It challenges our intuitive belief in the uniqueness of our reality, encouraging us to consider that our cosmos may be just one small patch within an infinitely varied tapestry. The concept of a sixth dimension, of entirely new universes separated fundamentally from our own, reshapes our philosophical understanding of existence. It invites us to contemplate the profound question of why we find ourselves within this particular universe, perfectly tuned to allow complex structures, galaxies, stars, and life. As we continue deeper into this exploration, we will unravel further how science approaches these enormous questions. The sixth dimension, with its infinite variety of entirely new universes, represents one of humanity's greatest intellectual leaps, pushing our understanding of reality to remarkable and previously unimagined horizons. As we continue exploring the sixth dimension, let us delve further into the fascinating science behind the concept of entirely distinct universes. The notion of separate universes, each with unique laws of physics, stretches our intellectual boundaries, compelling us to rethink what reality itself truly means. Physicists and cosmologists frequently consider why our universe seems perfectly fine-tuned for life. Slight variations in universal constants, such as gravitational strength, electromagnetic forces, or nuclear interactions, could render a universe lifeless, unstable, or radically different. This apparent precision has led scientists to speculate about a vast landscape of universes, each uniquely structured, existing simultaneously across higher dimensional space. In this cosmic landscape, universes can arise through a process known as eternal inflation, a scenario rooted deeply in modern cosmological theories. Inflation is the rapid exponential expansion thought to have occurred in the earliest moments of our universe. But in the eternal inflation model, the universe's expansion never fully ceases. Instead, pockets within the inflating cosmos continuously slow down, settle, and become stable universes, each potentially governed by entirely different physical laws. Imagine this vast cosmic landscape as an infinite ocean of inflating spacetime. Across its expansive surface, isolated bubbles, universes, emerge spontaneously, each bubble representing a separate reality. Within these bubbles, the inflating spacetime slows, settles, and forms stable environments, each governed by unique physical constants. Our universe, with its galaxies, stars, planets, and living beings, is simply one bubble among countless others. Remarkably, this eternal inflation model aligns neatly with the mathematical predictions from string theory and higher dimensional cosmology. Each universe emerges from the quantum fluctuations of inflating spacetime, acquiring its own unique characteristics from subtle variations in the structure of compactified dimensions and fundamental constants. These universes, once formed, evolve independently, separated by enormous stretches of inflating spacetime that keep them forever isolated from each other. Could we ever observe evidence of these distant, entirely separate universes? Theoretically, yes, but practically such detection poses significant challenges. Scientists suggest looking for indirect evidence within cosmic microwave background radiation, the faint afterglow from the universe's earliest moments. Certain anomalies or patterns within this radiation might hint at interactions or collisions between our universe and others in the early phases of their existence. While no conclusive evidence has emerged, cosmologists continue their careful investigations, understanding that even subtle clues could profoundly alter our cosmological understanding. Moreover, theoretical physics offers another intriguing scenario, the concept of baby universes, entirely new universes branching off from black holes within our own cosmos. According to some interpretations, when matter collapses into a singularity within a black hole, it may trigger the birth of a new universe, separated from ours, inaccessible, and governed by potentially different laws of physics. Thus, our universe might itself be the offspring of another universe, forming an intricate network of universes spawning universes, connected only through higher dimensional bridges hidden deep within black hole singularities. Beyond the realm of cosmological theory, philosophers also grapple with profound questions posed by the sixth dimensional landscape. If infinite universes exist, each governed by unique laws and initial conditions, what does this imply about our own significance or place within reality? The concept of countless separate universes forces us to reconsider deeply human concepts, such as uniqueness, purpose, and meaning, through a wider and more expansive lens. At its heart, the sixth dimension invites us to rethink reality as vastly more diverse, complex, and abundant than our intuitive experience suggests. It offers a radical expansion of our conceptual boundaries, a universe populated not merely by galaxies, stars, and planets, but by infinite possibilities and countless distinct realities, each valid within its own framework. Science, philosophy, and mathematics unite within the exploration of this remarkable dimension. Although we cannot physically traverse or directly observe these other universes, their theoretical existence profoundly influences our scientific and philosophical perspectives. They challenge assumptions about the uniqueness of our universe, enrich our cosmological understanding, and inspire new pathways of inquiry and exploration. In embracing the possibilities offered by the sixth dimension, we open ourselves intellectually to a vision of reality far more extraordinary and varied than ever imagined. The universe, and indeed reality itself, may be infinitely broader, richer, and more mysterious than we had previously dreamed. To grasp the true complexity of reality, we must now enter a domain where physics becomes deeply abstract, yet profoundly elegant, a place where space, time, matter, and force are not separate entities, but different expressions of a deeper, unified fabric. This is the realm of string theory. String theory begins with a radical idea that the universe is not composed of point-like particles, but of tiny vibrating strings of energy, so minuscule they defy direct observation. These strings are not metaphorical, but literal one-dimensional objects, each no thicker than the Planck length, the smallest measurable unit of space. And just as the vibration of a guitar string determines its musical note, the vibrational pattern of a fundamental string determines what kind of particle it becomes. One vibration gives rise to an electron, another to a photon, another to a quark. Every particle we observe, every building block of matter and force, is simply a different note played upon these tiny strings. But there's a condition. For the mathematics of string theory to work cleanly, consistently, and without internal contradiction, it requires additional dimensions of space beyond the three we know. Not just one or two more, but 6 extra spatial dimensions, giving us a total of 9 spatial dimensions, plus one of time, 10 dimensions. This requirement doesn't emerge from philosophical speculation or creative storytelling. It falls directly out of the math. Try to build string theory in only 3 dimensions of space, and the equations collapse into inconsistency. But add 6 more, and suddenly everything locks into place. These extra dimensions are not visible because they are believed to be compactified, curled up tightly at every point in space, like tiny origami folded into the very structure of the universe. If you are small enough, far smaller than any particle we've ever observed, you might see these hidden dimensions, wrapped delicately into complex geometries. One such geometry is known as a Calabi-Yau manifold, a name given to a specific class of 6-dimensional shapes with remarkable mathematical properties. These are not simple cubes or spheres, but intricate folded structures that can support the various ways strings vibrate. The shape of these compact dimensions determines the fundamental properties of the universe, the kinds of particles that exist, the forces between them, and the constants that govern everything from atomic stability to star formation. Imagine for a moment that each point in our familiar 3-dimensional space holds within it an entire 6-dimensional structure, infinitely small, yet infinitely influential. You cannot see it, touch it, or move within it, but it shapes the physics of everything around you. From the behavior of light to the mass of an electron, these invisible dimensions play a silent but profound role. It's not unlike the mechanics of a piano. You cannot see the inner strings when a key is struck, but their structure and tension determine the music that emerges. In string theory, the compact geometry of the hidden dimensions acts as that internal mechanism, defining the universe's tone, structure, and harmony. And just as there are countless ways to tune a piano, there are a vast number of possible Calabi-Yau shapes, each one leading to a different possible universe. Some allow for particles and forces like ours, others lead to strange, unfamiliar realities. In this sense, string theory doesn't point to a single unique universe, but to a landscape, a vast collection of possible realities, each emerging from different configurations of these hidden dimensions. The idea that the very identity of our universe, its structure, its forces, its ability to host life, emerges from the hidden shape of unseen dimensions is one of the most astonishing insights in modern physics. It suggests that reality is not built from rigid, indivisible particles, but from patterns, vibrations, geometries, and the resonance of strings stretched across a 10-dimensional stage. And so, the deeper we go into string theory, the more it begins to resemble music, an elegant mathematical harmony humming beneath everything we can see, everything we are. Let us now step further into this extraordinary theory and examine the implications it holds, not only for physics, but for the nature of reality itself. String theory is often called a theory of everything, not as a boast, but as a reflection of its bold ambition to unify all the forces of nature within a single, coherent framework. For over a century, physics has been divided into two great pillars: general relativity, which describes gravity and the shape of spacetime, and quantum mechanics, which governs the strange behavior of particles at the smallest scales. Each theory is beautiful, elegant, and powerful, yet they are fundamentally incompatible. Try to apply the rules of quantum mechanics to gravity, and the math breaks down into infinities and contradictions. Likewise, apply general relativity to the quantum realm, and its smooth geometry becomes turbulent and chaotic. The two frameworks speak different languages, and that has left physicists searching for a deeper language, one that can unite both realms. String theory offers that language. Within its framework, gravity is not an outlier. It is built in. One of the most extraordinary features of string theory is that it naturally includes the graviton, the hypothetical quantum particle of gravity. Unlike in traditional quantum field theories, gravity doesn't need to be added manually. It emerges effortlessly from the mathematics of vibrating strings. This unification is what makes string theory so compelling. It brings gravity into the quantum world without conflict, suggesting that all particles and all forces, electromagnetic, weak, strong, and gravitational, are different vibrational modes of the same fundamental object. Yet this elegance comes with extraordinary complexity. To describe the full richness of string theory, physicists often go beyond 10 dimensions. In certain formulations, particularly M-theory, an 11th dimension is added, extending the theory into a broader and even more mysterious landscape. In this view, strings themselves may not be the most fundamental objects. Instead, higher dimensional entities known as branes might take center stage. These branes can be 2-dimensional, 3-dimensional, or even higher, like shimmering sheets floating in higher dimensional space. Our universe, according to some versions of M-theory, could be a 3-dimensional brane embedded within a higher dimensional bulk. Everything we know, galaxies, planets, atoms, and even light, would be confined to this brane. Only gravity, with its unique properties, might seep into the higher dimensional bulk, subtly interacting with other branes and other universes beyond our own. This scenario offers a possible explanation for why gravity seems so much weaker than the other fundamental forces. If gravitational force lines are free to leak into extra dimensions, while the other forces remain trapped on our brane, then gravity's apparent weakness may simply be an illusion, an artifact of its dilution across more dimensions than we can perceive. And this, in turn, opens the door to entirely new ideas. If other branes exist, floating alongside ours in higher dimensional space, then collisions between these branes might spark dramatic cosmic events. Some physicists suggest that such a collision between two three-dimensional branes could have triggered the Big Bang itself, igniting the rapid expansion of space and time that gave birth to our universe. In this vision, our universe is not alone. It may be just one of many branes, each one a universe with its own distinct properties, suspended in a vast and largely unseen, higher dimensional arena. The implications are staggering. If string theory is correct, the universe is not built from indivisible particles, but from loops and membranes vibrating through dimensions we cannot see. The reality we experience is but a surface, an echo of deeper structures curled into the smallest corners of existence. And while string theory has not yet been confirmed experimentally, it remains one of the most mathematically consistent and conceptually complete frameworks for unifying all of nature's forces. Its beauty lies not only in its equations, but in the way it draws together space, time, matter, and force into a single symphony, a cosmic melody played across dimensions, with reality itself as the instrument. As we prepare to explore the 11th dimension and the mysterious world of Branes, we step beyond even the most abstract realms of geometry, into a domain where universes themselves can move, collide, and evolve, where space is not a static backdrop, but a living, dynamic fabric in higher dimensional motion. As string theory evolved, it led to an unexpected and profound realization. The theory was not singular. Instead, multiple versions emerged. 5 distinct formulations, each describing a universe of vibrating strings, each appearing different, yet mysteriously connected. For a time, this was unsettling. A theory of everything was expected to be unique, not fragmented. But then came a revelation. In the mid-1990s, physicist Edward Witten proposed that these 5-string theories were not separate theories at all, but different perspectives of a deeper, more fundamental framework, one that required an 11th dimension to fully describe. This deeper framework came to be known as M-theory. In M-theory, strings are no longer the only fundamental entities. Higher dimensional objects called branes, short for membranes, enter the picture. These branes can exist in various dimensions. A one-dimensional string is a one-brane, a two-dimensional surface is a two-brane, and so on, up to 9 branes and beyond. Some of these branes might be as large as entire universes. Our universe itself, according to this model, could be a 3-dimensional brane floating within an 11-dimensional bulk, a vast higher dimensional space that we cannot directly perceive. All the particles and forces we know, from electrons to photons, are confined to our brain, unable to escape its surface. Only gravity, with its ability to propagate through all dimensions, can seep into the higher dimensional bulk. This idea provides a compelling explanation for gravity's peculiar weakness. It may not be weak at all, it may simply be diluted, leaking into other dimensions we cannot access. The image is haunting and elegant. Picture our universe as a soap bubble drifting silently through a grand, invisible expanse. Nearby, other branes may exist. Parallel universes with different laws of physics, separated not by space as we know it, but by dimensions that curve and fold beyond ordinary sight. And though these branes may never meet, M-theory suggests they might occasionally collide. Such a collision, immense and violent, could unleash enough energy to create a new universe, a burst of space and time echoing outward like the Big Bang. Some theorists propose that this is precisely how our universe began, not from a singularity, but from the ripple of a higher dimensional impact. In this vision, the 11th dimension is not a distant abstraction. It is a hidden axis along which entire universes drift and interact. Time, space, matter, and even the origin of everything may be shaped not only by the physics of our brain, but by the unseen motion of others nearby. If our universe is a brane, one among many, then the 11th dimension becomes a stage for cosmic interactions of astonishing scale. Within this higher dimensional space, entire universes might float like leaves on a vast silent sea, governed by laws we are only beginning to imagine. These branes are not static. They can ripple, twist, vibrate, like immense sheets of energy suspended in the void. Their motion may shape the very structure of spacetime within them, subtly influencing the evolution of the universes they host. What's more, two branes may draw near one another, connected by the invisible gravity that permeates the bulk. And when they collide, something that may occur once every trillion years, or perhaps only once, an extraordinary release of energy could take place. This release, some theorists believe, is indistinguishable from a Big Bang. In this scenario, the birth of our universe wasn't a solitary explosion, but the aftermath of a brane collision, a higher dimensional event that set our cosmos into motion. And it may not be the only one. The universe might cycle through these collisions, expanding and cooling after each impact, only to reset again as branes rebound and drift apart. This idea, known as the ekpyrotic model, offers a vision of the cosmos not as a one-time event, but as part of an eternal, higher dimensional rhythm. It echoes ancient intuitions of cosmic cycles, now grounded in the mathematics of M-theory. Within this 11-dimensional framework, even gravity behaves differently. If it truly spreads into the bulk, it may offer clues we can observe, tiny deviations in gravitational strength, detectable in delicate experiments here on Earth. Physicists have already searched for such signals using precise torsion balances, hoping to detect subtle changes in gravity at sub-millimeter scales. So far, the results have upheld Newton's laws, but the search continues. M-theory, though far from complete, represents one of our boldest attempts to unify all physical phenomena. It weaves together quantum theory, gravity, strings and branes into a vast, elegant whole. It requires dimensions we cannot see, universes we cannot yet reach, and forces that flow beyond our brain-bound perception. And yet it may be true. What we once thought of as empty space may instead be a crowded, dynamic expanse, alive with motion, energy, and the silent drift of countless, unseen worlds. In the language of M-theory, the cosmos becomes a living tapestry, stitched not only with particles and waves, but with vast floating membranes, each one a universe in its own right, each shaped by the invisible scaffolding of the 11th dimension. Quantum mechanics is the strange heart of modern physics, a realm where particles behave like waves, where uncertainty reigns, and where reality does not fully exist until it is observed. It is also where the mystery of higher dimensions grows even deeper. At the quantum level, particles do not move like tiny billiard balls. Instead, they exist as probability clouds, smeared across space and time, occupying many possible states at once. Only when measured do they appear in a definite location, as if reality itself collapses into focus the moment it's seen. This bizarre behaviour suggests that our classical view of space, our familiar 3 dimensions plus time, may be incomplete. Hidden beneath the uncertainty and non-locality of quantum physics might lie a deeper, higher dimensional structure, an unseen framework guiding the probabilistic dance of particles. Some physicists have proposed that entanglement, the phenomenon where 2 particles become linked across vast distances, may hint at the presence of extra dimensions. Entangled particles behave as if they're connected beyond the bounds of space and time. Measure one, and the other responds instantly, even if light years apart. From our 3-dimensional perspective, this seems impossible. But if those particles are connected through a higher dimensional space, folded just beyond our perception, their instantaneous interaction might not violate physics at all. It would be like 2 points on a crumpled sheet of paper, far apart in 2 dimensions, but adjacent in a higher dimensional fold. This interpretation gains further weight from an idea known as ER equals EPR, a bold proposal linking quantum entanglement to wormholes. The equation suggests that every entangled particle pair might be connected by a microscopic bridge through spacetime, a quantum wormhole hidden in the folds of higher dimensions. If true, it would mean that the fabric of quantum mechanics is woven with the geometry of extra dimensions, and that the mysterious unity between particles is actually a reflection of deeper, topological connections we cannot yet see. It's an idea as poetic as it is radical, that the very strangeness of the quantum world, its unpredictability, its ghostly links, its refusal to obey classical logic, is not a glitch, but a window, a subtle glimpse into the true structure of the universe, one where the higher dimensions we've imagined are not just abstract math, but the silent architecture behind every electron, every photon, and every act of observation. The more physicists probe the quantum world, the more it resists a purely three-dimensional explanation. Quantum tunneling, for example, the ability of particles to pass through barriers they seemingly shouldn't cross, defies our everyday logic. Electrons can vanish from one side of a wall and reappear on the other, as if space itself had shortcuts hidden from view. In classical physics, such behavior would be impossible. But in a universe laced with higher dimensions, shortcuts are not only possible, they may be expected. A particle might take a detour through a curled-up dimension, bypassing obstacles in our visible three-dimensional space. To us, it appears as tunneling. To the particle, it may simply be the most efficient path through a higher dimensional topology. Quantum fields, the underlying fabric of particles and forces, may also be shaped by extra dimensions. In string theory, the different vibrational modes of strings depend on the geometry of compactified dimensions, but those same geometries could determine quantum behaviors as well, affecting probabilities, symmetries, and how particles interact. Even the elusive goal of unifying quantum mechanics and gravity may rest on the proper understanding of higher dimensional spaces. Traditional approaches have failed to reconcile the smooth curvature of spacetime with the granular chaos of quantum uncertainty. But in models with extra dimensions, particularly those inspired by M-theory, space and probability, curvature and entanglement are no longer separate ingredients. They are intertwined expressions of a deeper dimensional structure. In this framework, the randomness of quantum physics isn't truly random. It emerges from complexity we cannot see, like the ripples of an ocean whose depths remain hidden. Each particle's behavior is shaped not only by its immediate surroundings, but by the unseen folds and tensions of extra-dimensional space, tiny geometries influencing motion, energy, and fate. Some physicists even wonder if space-time itself is emergent, that is, not fundamental, but born from the collective behavior of entangled quantum systems. In this view, space and time arise not as starting points, but as consequences. The network of entanglement, the web of invisible connections between particles, gives birth to the structure we perceive as geometry. This idea, still speculative, represents a profound shift in thinking. It suggests that the familiar backdrop of the universe, length, width, height, and time, may be built from something else entirely, from information, from quantum states, from patterns and relationships existing in higher dimensional domains. And so the mysteries of the quantum realm, the uncertainty, the tunneling, the entanglement, become whispers of something more, hints that our three-dimensional perspective is not wrong, but incomplete, that beneath the probabilities lies a richer order, shaped by dimensions we do not see, yet feel in every measurement. To understand reality fully, we may need to lift our gaze beyond what is measurable, beyond even the particles, toward the hidden scaffolding of space, stitched together by higher dimensions and quantum threads, toward a deeper geometry, one that encodes all that is. For all the elegance and promise that higher dimensions offer, one question remains: if they exist, where are they? Physicists have spent decades designing experiments to detect signs of hidden dimensions, to glimpse those extra folds of space that might lie just beyond perception. If higher dimensions are real, they must leave fingerprints, subtle deviations in gravity, distortions in particle behavior, or patterns in the cosmos itself. One place scientists have focused their attention is gravity. Compared to the other fundamental forces, electromagnetism, the strong and weak nuclear forces, gravity is astonishingly weak. You can lift a paperclip with a fridge magnet, overpowering the entire gravitational pull of the Earth. Why is gravity so feeble? String theory and brain world models offer a possible answer. Gravity may not be weak, it may simply leak. If the universe contains extra dimensions, and most forces are confined to our three-dimensional brain, then gravity might be the only force able to spread out through the higher dimensional bulk. Like a spotlight shining through fog, it grows fainter the more space it must illuminate. This idea inspired a new generation of experiments. At laboratories around the world, physicists have built delicate instruments to test Newton's law of gravity at very small distances. If extra dimensions exist, gravity might deviate slightly from the inverse square law at sub-millimeter scales, growing stronger or weaker due to hidden geometric effects. So far, no such deviation has been observed, but the sensitivity of these experiments continues to improve. Each generation of data refines our understanding, closing off some theoretical models while keeping others alive. Another avenue of discovery lies in high-energy particle physics. At the Large Hadron Collider, deep beneath the countryside near Geneva, protons are smashed together at nearly the speed of light. In these collisions, physicists hope to produce particles that reveal signs of extra dimensions. One possibility is the creation of Kaluza-Klein particles, higher dimensional versions of familiar particles, appearing as heavier, excited states. Another possibility is even stranger, that miniature black holes might form in the aftermath of these collisions. If space contains extra dimensions, then gravity could become much stronger at tiny scales, lowering the threshold at which black holes can form. These black holes would evaporate instantly, leaving behind distinct patterns in the debris. No such black holes have been detected, but the search continues. Each result, each confirmed prediction or ruled out anomaly acts as a guidepost, steering the theoretical landscape. Higher dimensions may remain invisible, but their gravitational pull on our thinking has never been stronger. The search for higher dimensions has also reached into the deepest corners of the cosmos. If extra dimensions influence the universe's structure, they may have left subtle fingerprints in the cosmic microwave background, the faint afterglow of the Big Bang. This ancient radiation, still echoing across the sky, contains tiny fluctuations in temperature and density. Within these delicate patterns, scientists search for clues, anomalies that might reflect the influence of geometry beyond the visible three. Some models predict that during inflation, the rapid expansion that occurred in the first fraction of a second after the universe began, hidden dimensions could have stretched or warped unevenly. These warps might have seeded patterns in the microwave background that deviate from standard predictions. To date, these patterns remain consistent with three-dimensional space, but the precision of our measurements is improving. Satellites like WMAP and Planck have mapped the cosmic background with exquisite detail, and future missions may resolve subtler features, tiny asymmetries, spectral variations, or polarization patterns that hint at the presence of extraspatial folds. Even the shape of the universe itself is part of the search. In a universe with compactified dimensions, space could be wrapped in unexpected ways, looping back on itself, forming complex topologies. Light from distant galaxies might travel along multiple paths, arriving at Earth as overlapping images or repeated patterns across the sky. Such patterns could suggest that space is not infinite and flat, but curved and folded in ways consistent with higher dimensional theories. Astronomers scan the heavens for these echoes, testing whether the cosmic architecture includes features we cannot directly see. Each null result deepens the mystery. Are the extra dimensions too small, too curled, or simply not there? Some physicists suggest that higher dimensions might never be directly observed, but could instead be inferred through their mathematical necessity. Just as the existence of atoms was first proposed to explain chemical behavior, the existence of extra dimensions might remain unseen, yet still essential for unifying the laws of nature. Others believe we've only scratched the surface. New physics may emerge not from brute force experiments, but from unexpected domains, from quantum information theory, from gravitational wave astronomy, or from a deeper understanding of spacetime itself. Already, some researchers are exploring the idea that entanglement, not geometry, may be the true fabric of space, and that higher dimensions arise not from curled-up coordinates, but from the underlying relationships between quantum states. In this view, dimensions are not simply where things exist, they are how things relate. And so, the search for hidden dimensions has become more than a physical quest. It is a philosophical one, a pursuit of deeper understanding of what it means for space to exist and what lies beyond the veil of ordinary perception. We may never see a higher dimension with our eyes, but through mathematics, experiment, and imagination, we are learning to feel their presence, to sense the structure beneath the surface, to glimpse the shape of something vaster, quieter, and infinitely more intricate than the world we've always known. If there are hidden dimensions, and if those dimensions allow for more than one universe, then we must confront one of the most profound and unsettling ideas in all of modern physics, the multiverse. Not just one universe, not just one spacetime, but many, perhaps even an infinite number. This concept, once relegated to the margins of science fiction, now emerges naturally from several serious theories, each pointing, in its own way, toward a cosmos that is far larger, stranger, and more populated than anything we imagined. There is not one kind of multiverse, there are many. One version arises from eternal inflation, the idea that the rapid expansion of space never truly ends. In this view, our universe is a single bubble in an ever-growing froth of universes. Each bubble contains its own spacetime, its own laws of physics, its own version of reality. Some may resemble ours, others may be unrecognizably alien. In another version, rooted in quantum mechanics, every quantum decision gives rise to a branching of worlds. Every time a particle chooses a path, or a human makes a decision, the universe splits, each possibility realized in a new and separate branch of reality. This is the many worlds interpretation. In it, every version of you that could exist does exist, each one living out a different thread of possibility. Then there is the landscape multiverse of string theory, a vast field of potential universes, each corresponding to a different configuration of compactified dimensions. With millions, perhaps trillions, of possible Calabi-Yau shapes, each defines its own vacuum state, its own set of particles, forces, and constants. Our universe is just one point in this higher dimensional terrain. The implications are staggering. If the multiverse is real, then the physical constants of our universe, those delicate balances that allow matter to exist, stars to burn, and life to evolve, are not unique. They are not the product of design or inevitability. They are the result of cosmic chance, a lucky draw from an infinite deck of possibilities. And here, a subtle shift occurs. The question moves from, why is the universe fine-tuned for life, to, in which universes could life ever notice? We find ourselves here not because this universe was made for us, but because we can only exist in a universe where the conditions happen to allow it. This is the anthropic principle, and in the context of the multiverse, it becomes a powerful, if unsettling filter through which we must view existence. In this way, the multiverse doesn't just expand our physical horizon. It reframes the most intimate questions of meaning, identity, and purpose. It challenges us to consider that our universe may not be the whole, but a single thread in a vast multidimensional weave, a cosmos composed not of stars alone, but of countless realities, each hidden from the others, each real in its own right. Faced with such a vast possibility space, one naturally wonders, can we ever know if these other universes are real? By definition, most multiverse models describe realms forever sealed off from direct observation. The bubble universes of eternal inflation recede from one another faster than light, carried apart by the very fabric of space. The quantum branches of many worlds diverge in Hilbert space, mathematical, not physical distance, rendering them fundamentally non-interacting. And the vacua of string theory's landscape are separated by potential energy barriers we may never cross. Yet physicists search for indirect traces. If our universe once collided with another bubble, In the early stages of cosmic inflation, it might have left a faint circular bruise in the cosmic microwave background, a scar imprinted on the sky from a time before time. Observatories have searched for such signatures, and while none have been confirmed, the door remains open. Some theorists suggest that if we live in a brane world within a higher dimensional bulk, gravitational effects from neighbouring branes might subtly tug on our own, altering cosmic expansion rates, or even causing ripples in spacetime detectable as unusual gravitational wave signals. These signals too remain elusive, but our instruments grow more sensitive every year. More radical still are proposals from quantum computing and information theory, which suggest the fabric of reality may be constructed from pure information. In this view, the multiverse may not be a spatial expanse, but a computational structure, every universe a branch of an ever-expanding calculation, each consistent with the same underlying rules of logic. Here the question becomes not one of travel, but of structure. Not can we go there, but can we prove that their existence is necessary? Mathematically, some frameworks suggest that a universe like ours, with stable atoms, long-lived stars and complex chemistry, is extraordinarily rare among all possible configurations. Its very rarity hints at a wider set of possibilities, a cosmic ensemble from which our pocket of reality is drawn. This idea reshapes not only cosmology, but meaning. For in a multiverse, our universe is no longer central. It is no longer privileged. It becomes one of many. And perhaps that humility is its own form of beauty. We become not isolated miracles, but expressions, a fleeting pattern in an infinite sea of variation. Our atoms, our thoughts, our moment of quiet reflection here are all part of something far larger than any single cosmos could contain. And in this way, the multiverse is not a cold abstraction. It is a profound invitation to see ourselves differently, to recognize that we are part of a far greater tapestry, one woven with infinite threads of possibility and patterned by the mathematics of higher dimensions. And now the journey winds to a close. We have wandered through the invisible scaffolding of reality, past the familiar axis of space, through the flowing stream of time, and into the vast unknown realms of higher dimensions. We have imagined curled geometries beneath every point in space. We have explored the soft drift of Branes in the 11th dimension, and we have stood at the edge of a multiverse, our single thread woven into a fabric of infinite possibilities. What began as a simple question, what lies beyond the dimensions we see, has grown into something deeper. Not merely a tour of abstract mathematics or speculative physics, but a shift in how we understand ourselves. In the silence between dimensions, something extraordinary emerges: perspective. We are no longer at the centre of the cosmos, but part of its endless branching. No longer confined to one flat view of reality, but aware, gently, humbly, of the depth that lies behind the veil. Even if the extra dimensions remain forever hidden to our eyes, they have expanded our minds. They have taught us to listen more closely to the universe's quiet architecture. And perhaps that is the greater gift, to realize that space is not empty, but structured, that time is not absolute, but woven, that we too are not separate from this grand design, but part of it, made of strings, of fields, of vibrating dimensions, folded within every breath. Maybe you will forget the names: Calabi Yao, M Theory, Kaluza Klein. That's all right. What remains is the knowing, a stillness shaped like wonder. As you return now to the quiet edge of sleep, carry this dream with you, a dream of hidden corridors behind every star, of invisible loops curled beneath your fingertips, of a reality far vaster and more mysterious than the surface ever reveals. We are beings of 3 dimensions, wrapped in 4, drifting through 10, born from 11. And in that unfolding, infinite as it is silent, we are home.